So good morning, good afternoon, good evening, good night to all of you. Welcome to the second lecture in the Nearing lecture series. Last time we have already defined what a nearing is. We have seen some examples. We have seen uh, what the zero-symmetric and what the constant parts are, and we also mentioned that nearings arise naturally when you study nonlinear contexts. And the transition from rings to nearings is in fact the transition from linear to nonlinear situations. And if you think of the difference between linear and nonlinear in various areas like differential equations, like in systems theory and so on, you know that the transition from linear to nonlinear is everything else than easy. And so it doesn't surprise us that we uh, face some difficulties. Some things are much more difficult than in ring theory. But on the other hand, there are also some pleasant surprises, namely that many things can also be done for nearings uh, instead of rings. And however, the way how to do this is different from ring theory. And during the course of these lectures, it will be becoming interesting to find out that the rather harmlessly looking class of nearings has a surprising number of applications. We'll go into more detail in two areas, namely in applications for near fields and in the applications for planar nearings. We have seen last time also that every nearing is composed of its zero-symmetric part and its constant part. And so we can write n always equal to n sub naught plus n sub c. N sub naught is the zero-symmetric part consisting of all elements which fulfill that n times 0 is equal to 0, and nc is the constant part of all elements n which fulfill n times 0 is equal to n. And moreover, this intersection of n sub naught and n sub c easily turns out to be 0, because if some element fulfills n sub naught is equal to naught, and n sub naught is n times naught is equal to n, then n must be 0. And so we have almost a direct sum, but it's not completely a direct sum, and we'll find out more about this later on. Oh yeah, we are in section 2. Simply nearings. More precisely, the elementary part of nearings. One, n is a semi-direct sum of n sub naught and n sub c. As mentioned last time, n sub naught looks more like a ring. It's more ring-like, and n sub c is just the additive group with a trivial multiplication. A times b is equal to a for all a and b. And so we have a rather more ring-like part and a rather more group-like part, and n is a mixture between these two between these two classes of structures. The most common example of a nearing is the nearing of the set of all mappings from a group G into itself. Again, this is the set of all functions f going from G to G. And here we write G plus in a group additively written, not necessarily abelian. The addition of functions is the pointwise addition, and the multiplication is the composition of functions. Now, this M of G turns out to be a very important class of nearings in the following sense. Take any nearing N and take a group which contains N plus as a proper subgroup. Take a group G such that N plus is a proper subgroup of G plus. Then we might consider the following map: phi going from G from N to M of G by sending each element N to some map phi sub N. And this in turn is defined in the following way, that it maps from G to G in such a way that an element G will be mapped into N composed with G in the case that G is in N, and it will map into N otherwise. So we see that we have a map from N into M of G. Phi sub N actually is a map from G into G, constructed in this way. And if we find out what phi has to offer, we can say if we take a sum here, N1 plus N2 instead of N, then we get N1 plus N2 here, and N1 plus N2 here. And so we see immediately that phi is an additive homomorphism. What about the composition, N times M? Then we have phi N times M, and that maps G into N times M times G, or into N times M. And again, you can see that this is just a composition of phi N and phi M. That's not only homomorphism, but it's an injective homomorphism, because what happens if we take N1 equal to N2? So phi is injective if N1 is unequal to N2. What about phi sub N1 and phi sub N2? Will they be equal? Well, if we map if we apply this to some element G outside of N, which must exist, according to this requirement. So this of G here is unequal to phi sub n2 of G, because this is, if G is not in N, this is just N sub 1, and this is just N sub 2. And so by this trick of enlarging the additive group of N just a little bit, we reach the injectivity of this. And then we can say that N can be embedded into M of G, because we have an injective homomorphism from N into M of G. And so we can find an isomorphic copy of N inside of M of G. We can summarize this here as follows. We can say, so every nearing N can be embedded into, or in some M of G. In this sense that for every nearing N, we can find a group G. Actually, we can choose among plenty of them, so that N can be embedded into this. And the same applies if we take a zero-symmetric nearing, then we can embed it into M sub node of G, and every constant nearing can be embedded into some MC of G. Those are constant mappings on the group G. Sometimes one calls this or expresses this, that the class of nearings of the type M of G is Catholic, which means containing everything in some way, because every nearing can be embedded into one of those. That's in the same way as in group theory. Permutation groups are Catholic because every group can be regarded as a subgroup of some full permutation group. This shows even more, because as a corollary, we can say that every nearing N can be embedded in a nearing with identity. Because M of G has an identity, namely the identity map. Now observe the proof of this result, that every nearing can be embedded into some M of G, is different from the corresponding proof for rings. For rings, it says every ring can be embedded into the endomorphism ring of some group G. And here you see again, in the ring case, we have endomorphisms here. In a non-ring case, in the general nearing case, we have arbitrary maps from G to G. Again, this shows that here we have a nonlinear situation. And also the proof that every ring can be embedded into a ring with identity does not work for nearings. We have to find this completely different proof. And in fact, it's even easier to show, because it comes as a corollary, that every nearing can be embedded into a nearing with identity. However, in rings, we can say a little more. We can say that every ring can be embedded into a ring with identity as an ideal. Here we cannot say this, and Gerhard Betsch, who is among around, has shown once that not every nearing can be embedded as an ideal into a nearing with identity. Now I have mentioned ideals, haven't defined it yet. It will come in a few minutes. In fact, being a nearing with identity is something special, also something which Gerhard Betsch has mentioned several years ago. And if you look at the list of nearings of low order, then we found out that up to the order 32, only 1% of all nearings have an identity. So it's really rather rare for nearings to have an identity. Something which inevitably has to come in the case of elementary theory of algebraic structures is the thing with the substructures. Now, in the case of substructures, the first thing which comes to your mind will be, I think, subnearings, and it's clear what it means. A subset of a nearing is a subnearing if it's itself a nearing with induced operations. Not so easy and immediate is the thing with the ideals. If we look at back at our early childhood, when we learned about vector spaces in the first year of university, we also knew that every vector space has subspaces, and if a vector space V has a subspace W, then the subspace induced an interesting equivalence relation in the following way, that if we have two vectors v1 and v2, they are equivalent with respect to this subspace W if and only if the difference v1 minus v2 is in this subspace. So if you consider W as, say, as a small subspace, it means that v1 and v2 differ only by a small element, so to speak. And this means that v1 and v2 are equivalent with respect to W. And it turns out that this relation here is not only an equivalence relation, which can be seen immediately, almost, it is also compatible, which means that if you have another pair v1 prime, which is equivalent to v2 prime, then the sums v1 plus v2 is equivalent to v2 plus v2 prime. And if these are equivalent, and if you take a lambda in the field over where the vector space is formed of, then lambda times v1 is also equivalent to lambda times v2, which means that this is an equivalence relation which respects both addition and the multiplication within the lambda. Now, if we have a nearing n, we might have a similar situation. So if you have a nearing n, and some subnearing M, which we denote in this way. So it's not only subset, this means subnearing. Then we again might define an addition, an equivalence relation in the following way, that we say if we have two N1 and then N2, they are equivalent with respect to M. Again, if their difference N1 minus N2 is contained in this subnearing M. Now we might ask, of course, now is this an equivalence relation, and that can be shown in the same way as for vector spaces. The more interesting question is this relation here compatible with the nearing addition and the nearing multiplication? Now, compatible with the nearing addition means that we have the same situation, that we might think back of group theory with a subgroup of a group, and we can form the same relation here, and we can say that this here is compatible with plus. That's a group theoretic question. We know the answer if and only if M is a normal subgroup of N. M plus is a normal subgroup. We denote this in this way of N plus. And when is it compatible with respect to multiplication? Well, in this case, we have to work a little more. And we have to find out when this will be the case. So let's simply test this thing to move forward. Suppose we have N1 equivalent to, with respect to M, to N2, and N1 prime is equivalent to N2 prime. And we would like to find out when is N1 prime equivalent to N2 times N2 prime. Okay, we can translate this into what we had. N1 minus N2 must be in M, and N1 prime minus N2 prime must be in M. Now M was supposed to be a subnearing, so we can say, okay, the product of these two things here must also be in M. However, it's not as easy as in ring theory to work out this, because what we have now is, due to the lack of one of the distributive laws, we can only say a little less. We can say that N1 times n1 prime minus n2 prime minus n2 times n1 prime minus n2 prime is in M. We cannot use the other distributive law, and so we see that things are not that easy. We have, if it were a ring, if we had the distributive law here, we had n1 times n1 prime in M. Okay, that's the second thing. And then, then it goes on, but we are not in ring theory, so we do have to work a little more. And one can easily show, and we could do this perhaps in the sense of an exercise, that we can say that n1 minus n2 times n1 prime minus n2 prime is in M, if and only if, and the condition is now twofold with two conditions. The first is easy and can be easily expressed in such a way that for all now let's say now A, B in N, and for all let's call it M in M, we have the following condition, that A times B plus M minus A times B must be in M. That's called as condition 1. And for all A in N and for all M in N, we have the condition that M times A must be in M. So that's condition number 2. You can see here, if we would have a distributivity of A, we could simplify this to AB plus M minus AB, which basically means that A times M must be in M. But this is some other condition, and we cannot simply do this. And we have a condition which is a little more involved than the condition for near-rings. So all together, when is this relation here compatible with addition and multiplication, if and only if first M plus is a normal subgroup of N plus, and if these conditions hold. In this case, we call M an ideal, and we then write M is an ideal of N. If and only if, as I said, M plus is normal. and with conditions 1 and 2. In this case, we write it in the sense M is an ideal of N. If we have an ideal, and if we only have 1 or 2, we call this a right ideal of N if and only if M plus is normal and we have condition right ideal. If we have condition this here, the 3 times, normal, and we have condition 1, and it's called the left ideal if we have normal and condition 2. So these two are called one-sided ideals, and if it's a left and right ideal, it's simply called an ideal. Now it's perhaps time again, as last time, to have some questions, some materials for exercises, and we will be as follows. Question 5. Find the subnearing M of N. Is a proper, okay, with the property that M is not an ideal of N. And question 6, find a left ideal which is not a right ideal, and conversely. Perhaps I should give a few, or at least one example. Let's take, because it's by far the most important example, let's take M to be M sub naught. But let's do it more general. Just as an exercise, M sub naught is always a right ideal of a near-ring N. It's always the case. Why? M sub naught is a normal subgroup. Why is it normal? Excuse me, Mn sub naught is right ideal. let's take n to be an n, and let's take m to be in n sub naught. What about n plus m minus n? It should be again in naught. So what we have to do, we simply have to apply 0 to it. This is equal to n times 0 plus m times 0 minus n times 0. Now m times 0 is equal to 0, and you see it ends up not n times 0 minus n times 0, and so the result is equal to 0. So n sub naught is in fact a normal subgroup. We have the first of these requirements, and then we look at the second thing. What about the condition number 1? Suppose we have, let's call the elements now A and B, A, B in N. And let's take M to be in N sub naught. And we have to take care of what A times B plus M minus A times B does. Our hope is that this is again in N sub naught. So we apply the same check as before. We ask what happens if we take this here times 0. Now this is equal to A times B plus M times 0 minus A B 0. Now we can switch, we can look at this here. We can multiply this out. So we can say we have A times B times 0 plus M times 0 minus AB 0. Now again, N times 0 is equal to 0. And what do we have? We have AB 0 minus AB 0, so equal to 0. And so it means that this more complicated expression is in fact again zero symmetric, and so we have that N sub naught is a right ideal. You might test if it's a left ideal also, and that's the content of question, where you can settle question 6 partly with that. Maybe I might mention an open problem here in this area, which is still unsettled, and that's the following thing. So the following problem is open. Does there exist a near-ring N with identity whose additive group is simple? Near-ring with identity. Let's call the near-ring N with identity such that the additive group of N is a simple group. Well, you know that that does exist a near-ring with such a property. For instance, take a finite field where the additive group is simple, a finite prime field, and then you have an example of this. But I mean, of course, an example of a real a non a non-field a proper nearing with these properties. There exists an old result by Clay and Malone, saying then that if such a nearing exists, that n must then be infinite. Unless it's a finite prime field. So in this case, we can say we must have an infinite simple group, and you know there do exist some classes that one knows in some sense what happens in finite simple groups, but not in the infinite. They are much more difficult and not really characterized. Now let's get back to the theory, and if we take a nearing n, and if we find an ideal, then we can construct a new nearing out of that. So if, let's call it now I, is an ideal of n, two-sided, then we can form the equivalence classes, namely we call it n factored by I. It contains all sets of the form n plus I with n and n. And n plus I means the set n plus small I, where small I is in capital I. And the operations are the following: n1 plus, let's say n plus I plus m plus I is defined as n plus m plus I, and the product here is defined as n times m plus I. You need an ideal so that to make sure that these operations are well defined. They don't depend on the representative of this coset, cosets here. And in this case, you get a so-called factoring n factored by I. Occasionally, it might be that you have a nearing and you have very few ideals. Now, you always have two ideals. One is 0 itself. So 0 alone is always an ideal of n. And n itself is also always an ideal of n. So these are the two trivial ideals. That happens in every class of algebraic systems, which is comparable. And if you have no others, no interesting ideals, we call a nearing simple. So if these are all ideals, we call the nearing n to be simple. You know that in group theory, in some way, at least all finite groups can be made up in a certain sense from simple groups, and they are characterized in the case of rings. Uh, while you one has no control of simple rings, but if they have an identity or if they behave nicely with some finiteness conditions, one knows how they look like, and they play the perhaps one of the most important role in ring theory. Interesting is the following theorem. We cannot prove them right now. We will return to uh, one of these later on. They are due to Berman and Silverman and Malone. And I give three statements. The first thing is that M naught of G is always simple. So it's, despite the fact that it's a real big nearing, but it's simple in the sense it has no non-trivial ideals. What about M of G itself? This is simple if and only if the group G uh, has not exactly two elements. So except in one occasion, when G is the two-element group, it's not simple, but in the case of all other groups, also M of G is simple, and in fact, M of naught is pretty uh, high in the order of sub-nearings, namely in the following sense that there is no sub-nearing between M sub naught of G and M of G. Uh, there is no sub-nearing N strictly between M sub naught of G and M of G. So no further nearing N fits into this gap between M sub naught of G and M of G. Now maybe we look at this exceptional case here where G has just two elements. And in there, we do have one ideal, and this is itself, of course, a subnearing, and it's the smallest nearing on Earth which is not a ring, and it can be seen to be the following nearing. Let's define it as M sub C, the constant nearing over the two-element field. This here is really an ideal in M of Z2. Now let's look at the sizes. M of Z2 are all functions from Z2 into Z2. They are not awfully many of them. They are just 2 to the 2 to we have here four functions, and MC of Z2 must have two elements, and the multiplication of this is very easy. The multiplication of MC of Z2 is the following: we have 0, 1, 0, 1, and the product is always the first element. So it's always here 0, 0, and here 1, 1. And in fact, you see, this is a rather trivial example of a near-ring, but you might say it's the smallest near-ring on Earth. And the addition is simply addition modulo 2. And so it's called maybe the baby of all of these near-rings. Now let's perhaps end this with a short look to other related structures. One of these related structures are so-called semi-near-rings. Semi-near-rings differ from near-rings in the fact that the additive group doesn't have to be a group, just a semigroup. So you have additively a semigroup, you have multiplicatively a semigroup, and you have one of the distributive laws. Now you might say that's a creature which never shows up in nature, but it's not true. Similar to the case of M of G, we have examples right at hand. For instance, take all the natural numbers and take all the functions from the natural numbers into itself with addition and composition. Then the additive group is the additive group of all functions from n to n, which is not a group, it's just a semigroup, and we have just one distributive law. You might call this a very natural example because it's the set of all functions from the naturals to the naturals. That's the topic of number theory, and you get a very decent example of a semi-near-ring there. You find other structures which have only one-sided distributive elements in many areas, including physics. And one of the member in our group, Mr. Henschenmacher, found this in an early paper of Pascal Jordan, and maybe Mr. Henschenmacher will give us an account on these connections later on. So we do have now a good basis to proceed to more detailed topics. And the next section 3 next week will be on near fields. These are near rings where the multiplicative semigroup actually is a group as well. And we'll find that these near fields do have a interesting history, and also they have an interesting theory and a number of applications where one would not think of in the beginning. So hope you stay well for the rest of this week, and I hope to see you again next week, same time, same station. Bye-bye.